Hello. Today I decided to do a quick video about Pile. As I understand, there is a lot of misunderstanding. I received a few comments on uh, in the emails and coming from a YouTube videos about what we did with the Pile. Now, a Pile is a custom memory manager that we have created. It is 100% managed code. Let me repeat that. Pile is 100% managed code. It does not use any C++ or C. It is written in the sole programming language, which is C sharp, and there are no other programming languages involved. You can get the code at GitHub if you look for OM code. That is github.com/OM, A-U-M, code, C-O-D-E, slash NFX. So the Pile is a part of our NFX project, but it is 100% managed code. What is a pile? A pile is a synonym to the word heap. In English, for those who may not know, because I have some people who are not native English speakers, the word pile is a similar word to the word heap in English, which is just a mound of something, like a mound of debris or dirt or, sand on the beach, on the sea shore or something like that. So a pile, I use the word pile to have the similar notion, the similar sense that the word heap, has, but to differentiate between the two. So the pile is the memory manager, and it allows us to allocate objects and free the managed garbage collector in .NET from having to deal with these objects. Now, what the hell are we doing? Why do we do that? We do that for the number of reasons, but first and foremost, is the ability to allocate lots of objects and have them resident in memory for a long time. This is needed primarily for caches, for caching of your business data in your web applications, especially in the social driven web scenarios when you have social comments peppering at you like at the rate of, let's say, 1,000 comments a second coming from different sources, and or your users want to look those comments up. They come to the page and they want to load the discussion thread under your page, and what it's used for, let's say you have a product and you have many products, and every product has a thread, and every thread has thousands of comments in there, and you want to load those comments quickly. From where? From the database. That is very slow. From the external cache, you can do that, you can load them, but that is way slower than keeping that stuff in RAM. Now, if you keep that stuff in RAM, you are going to hit the wall straight. The wall is the garbage collector. Garbage collector in .NET defragments the RAM. That is, it takes the holes in RAM and it gets rid of them and it shifts everything. And at least it does it for the small objects like that are smaller than 86 kilobytes or something. And in the new version of .NET, there is even an option to start the garbage collection for the large object heap. But still, we don't want to move many large or even small objects around, because when we move them, we need to adjust all of the pointers that point to the place where the objects are in the RAM. So what we did a custom memory manager that alleviates all of these problems by basically allocating a huge, let me draw it for you guys because it'll be easier. Let's pretend that we're in the all days classroom with a blackboard, only that's a whiteboard, and we have a piece of chalk. My chalk is going to be black here on the whiteboard, okay? So what we do, we allocate a large byte array, and then we sub-allocate chunks of that byte array, and we hand it off to the user. So the user of the pile comes in and says, here is a .NET object. Here it is. Here's my object. I want to stick it in the pile. What the memory manager does, it finds the space, and here it is. It found the space. And it squeezes this object in there. But first, it transforms this object. It serializes it to an array of bytes. Okay? It turns it into an array of bytes. And then it stores this array of bytes in a pile. Now, you may say, oh, this is so slow. Before you jump to conclusions, hear the whole story out. First of all, what you have to realize that in NFX, we have built a very efficient serializer called SLIM. It is similar to Microsoft Binary Formatter, only it works many times faster than Microsoft Binary Formatter, and this is not a bullshit statement. I have some real evidence to support my claim here. We go to GitHub and we look at the Serbench project, which is, the little project we did just to as a proof of concept of serializers. Serializer benchmark. There is a site right here. The Serbench project, it runs different serializers against different payload patterns. You see, we do all kinds of crazy stuff. We do even EDI, X12, 835 government, remittance claims and all of that crap. But what's good about it is that it generates the report that you can see right here. Those are different serializers, and those are different performances, and those are different payload sizes. And we also color code them, and then we also log the aborts. Okay, what has been aborted, or what, crashed with a try-catch, or whatever. So, the SLIM serializer is an extremely efficient serializer when it is warmed up. It is in the same league as the protocol buffers, and as far as the size, you see that? This is our serializer on the typical person. This is a case of a typical person, like a typical business payload. First name, last name, city, state, zip, addresses, all of that stuff. Email. And then we do a single person, we do a list of 100 people, and we do a list of 500 people, and we see how different serializers can take it. But I don't want to go, I'm going to do a separate video about this stuff, But what I want to say here is this. So our serializer is very fast, okay, especially in the scenarios that it was built for use in the pile, which is called batching, okay. We call... let me show it to you real quick here. We have a special mode called batching that many times we outperform even protocol buffers in in the performance here. And the reason for it being protocol buffers is a very, very well put serializer by Mark Gravel. That is protocolbuffers.net by Mark Gravel. Very good serializer. But it doesn't understand polymorphism, and it does not understand dynamic types and a lot of stuff because it was not built for it. SLIM serializer does. So what this allows us to do, basically, why I show it to you, because the video was about the pile. This object that we want to serialize, it can be any object. It does not have to be decorated. It can be a tuple of string, or it can be a dictionary of string, list of string, or something like that with invariant culture comparer. For those of you who don't know, the dictionaries, and especially concurrent dictionary, they are serializable in .NET. You can serialize dictionaries. As a binary serialization mechanism, you can. But the problem is Microsoft Binary Formatter, it is very slow. It is very safe serializer because it does a lot of security checks, but it is very slow. The SLIM serializer works on average 5 to 10 times faster than Microsoft Binary Formatter because it calculates, or it compiles the expression trees used for object serialization and deserialization. So what we do with the pile, we serialize it in a byte array. Okay, here is our byte array. Let's put a different color here, okay? And then we stick this byte array here. Okay, and then the pile remembers it. So the pile, every little segment here has a signature right here, and it can crawl this large segment. This whole block is about 200 56 megabytes in size. Okay, and we call this a segment. And then the index within the segment is actually the address of the object. So what we get as the result when we put the .NET object in there, we get something called pile pointer. The pile pointer is basically a tuple of int segment. If I could type, okay, been only doing this for 30 years, I still can't type. God damn it. Okay, segment, and then there is another one called address. Okay, so this is the pile pointer, and it is a struct. Okay, so it does not induce any pressure on the garbage collector. You can dereference the pile pointer back to the original object. So what this guy is going to do, it is going to take that and it will deserialize it and give you the original object back. A different object, of course, in terms of pointer. Let me explain this. The object that you are going to get back when you read from the pile, it is not going to be this object in terms of reference identity. It is a different reference, a different location in memory. But it is the same object. It has the same data that you put in the pile. So the pile then, you can think of it as a special kind of database that you run within your process. It's like this, like database, okay? Where you can put objects and you get the pile pointer back, and then the pile pointer, you dereference it, and you get, by the pile pointer, you get back your original object that you have serialized. And because we use Slim Serializer, it is fast. How fast, I'm going to show you in a second, and it is very capable in terms of supporting nested types, polymorphism, interfaces, all kinds of stuff. The only thing we do not support, we do not serialize delegates, okay? We do not serialize events. But in my practical experience, this is rarely needed, if ever. So what we use Pile for, we store those circuitous, object graphs like this, that may have a parent and child may look back at the parent, and all of that kind of crap with cyclical references and everything. This is all stored here. Now, an interesting observation, the Slim Serializer compresses the object to the hell out. So that, this little chunk, what I call, a chunk within the segment, is usually less in size, in byte size, than this in the memory. Why? Because every .NET object has a header that contains what? It contains the CLR flags for locking and different garbage collector flag and all this kind of stuff. Plus, it stores information about fields or primitive types in an uncompressed format. That is, integer takes 4 bytes, blah, 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 long takes 8, and what Slim Serializer does, it does the adaptive compression, that is a bit variable encoding for integers and integer arrays. So let's say you have an array of 1,000 integers. Instead of taking 4,000 bytes, it will only take 1,000 bytes. Why? Because if those integers are 0, they're going to only take 1 byte. You know what I'm saying here. So this compression, the cost of this compression is almost nonsensical, or rather non-existent, because it is very fast, okay? So, and when you deallocate something from the pile, this block gets written back to the free buffer list. So every segment has a registry, so to speak, a list, a set of lists for the free buffers, where it keeps the indexes of what is free, every list here. And I'm drawing this like it looks horrible, but I hope you guys understand what I'm trying to describe here. So every list here, so let's say this block has been 37 bytes. So it tries to find what is the, okay, here, this block is 35 bytes, this is 37, so the index of this block is going to be entered here. And the way how this free lists work, they pre-allocate this structure in RAM. So everything is done here not to induce any pressure on Microsoft Garbage Collector, which is a phenomenal piece of software. If you think about it, what Microsoft did, and not only Microsoft, let's say that Java does it very well as well. But the problem is you cannot have 300 million objects in your heap, no matter how clever your garbage collector is, because 300 million objects, that's just a lot of stuff. Now with Pile, we don't have to visit them by the garbage collector because we do it internally. So here is the deal. Every time you allocate, it creates this array, and it says, okay, so the serialized thing here is 87 bytes, let's say 37 bytes, like I used before, 37 bytes. Where the hell am I gonna stick it in here? So of course it uses those free indexes to find the most appropriate slot, and if it can't find it, it just returns it and occupies it. And it writes a little header here, okay, that this slot is taken. Now, if there is no space in indices, it may, depending on the situation with multi-threading and everything, go to the next segment and try to find space there. After it reaches some threshold, it starts crawling the segment. So that is the crawl operation. It will visit all of the holes. So there is fragmentation possible because you delete the data just like you do in C++. Or if you're a good C programmer and C++ programmer, you understand what a memory fragmentation is. This is good because we wanted Pile to allow us we don't want memory fragmentation, but we wanted to create a memory manager that does not shift pointers. So it allows us to store 300 million objects. So yes, we do have fragmentation, but in the practical world, this fragmentation is absolutely all right because you delete some information, then you repopulate, and you have some free chunks, just like with your hard drive. You have files of different sizes, you would always get fragmentation. But it doesn't mean that you cannot use hard drive. Of course you can. That just means if you create a file which is 2 bytes in size, you can occupy that many bytes on the sector on the hard drive. Same concept here, okay? So, let me repeat. You have an ability to delete information that you put in the pile and release this memory. Is it possible to have a memory leak in the pile? Absolutely it is. That's the whole point of the pile. The pile brings a unmanaged memory paradigm, so to speak, into the managed environment. This sounds a little bit crazy. You may say, hey man, what are you smoking there? And let me tell you, this was done on purpose. Because there is a set of tasks that would really benefit from having unmanaged memory, and one of them I described to you. That's a cache-like operations that we need to execute. Let's look at this API. This is an interface. It has a put method, object, and optional lifespan. Not all of the piles are obligated to support lifespans in seconds. Okay, but you get a pile pointer back. Let's hit F12, see what the hell that is. The pile pointer is equatable of pile pointer. It's basically 3 things. It has node ID. Let's skip that for a second because our piles can span many computers in the cluster. But let's skip that for a second. We have a segment and an address. So that's what it has. And the segment is the number. We can have multiple segments. The piles allocates more segments. Those are like those large chunks, okay? And the address is the offset within the segment. So that's very simple. Now, where was I? You get pile pointer, you get either access violation, or you get an object back. And then you get a delete. Delete gets a pointer, and then this is a handy tool because sometimes you can have stale pointers. You cannot get a stale pointer, but you can get a delete that would return false. I don't want to have any exceptions. Exceptions, for those of you who don't know, exceptions are usually 10 times slower at least than returning a Boolean flag. In many cases, it is very easy to throw an exception and then, oh, what the hell? I had 300,000 requests a second. Now I'm down to 25,000 requests a second. Those are your exceptions. If you're throwing too many exceptions on the regular basis, that may be really slowing everything down. You'd better, return a Boolean flag and put an if statement. That would work 10 times faster at least. And again, you just have to take my word for it or go write a simple test if you don't believe me. Rejuvenate is used to rejuvenate an object pointed to by the pile pointer. For those of you, for those objects that have lifespan set. You can rejuvenate the object. Size off gives you the size of an object in bytes that you are pointing to. Purge deallocates everything, and compact tries to reallocate and get rid of extra space and release the space. Release the space back to the operating system. Okay. So where is the implementation of this interface? It's all in one file. And this file is only 1,400 lines of code. Okay, let's say 1,500 lines of code. And it has very extensive instrumentation about object count, segment count, allocated memory bytes, utilized bytes, memory capacity bytes, overhead bytes, all of that stuff. So this is all instrumentable. And what is instrumentable also, the free, you remember I showed you the free lists. So that is instrumentable as well. You can see that in the graphs. Okay, and how you instrument stuff, how you visualize, we can talk about it some other time, but the pile is configurable. All of these numbers are tunable. You can put it in the configuration file and fine-tune it to your particular case. Those are your chunk markers, for the use chunk and free chunk. And this is the whole thing. The pile is a 100% thread-safe, multi-threaded solution. So you can run it on a web server, on the multi-threaded web server with task parallel library, with async, await, or whatever you call it, with all of that stuff. The pile does not expose any asynchronous APIs, and that is done on purpose because really the pile is usually not an I/O, it is a CPU-bound operation, okay? And what it does, it does a lot of memory, it does a lot of CPU, serialization and everything. And practically, I never needed any asynchronous APIs. We could probably put them in future, but the practical reason for it is not there. Okay, for the distributed pile it may be, but again, not for the resident pile, for the default pile, which is a pile that you allocate in your address space. Now, a few words about synchronization. Everything is done as much as possible in the lock-free manner, not to lock on things, like multi-read, exclusive write, synchronizers, and all of that crap. The pile is thread safe, though. It does use the lock, and the lock that it uses is from here. Many readers, one write synchronizer. Now, this is a very advanced topic, and let me tell you something. Before we wrote this class, we used different patterns. We used Microsoft class. So after we did a lot of benchmarking with, reader-writer lock slim, and then we used another library that we benchmarked was Wintellect, I think it's called. That's one of the I think Geoffrey Richter or something, the guy from the Microsoft. That's his company, I think, Wintellect. And I think they have some open source that you can try out. So we did a lot of benchmarking, and it turned out that our solution is better. It yields better results. So this is a very advanced topic here that, basically instead of just releasing the control to the operating system scheduler, thread sleep, that is, it does a tight spin, tight one pause, and what it does, it tries to, in some cases, slip one or slip zero, and then it tries to yield, and then it tries to spin wait. And those numbers where, we played with the different numbers. This is an advanced topic. I'm just showing to you so you understand that what this class does. It does a spin wait that is a very tight loop, and it tries to gain the access to resource, okay? That's internal implementation detail. The default pile uses it to synchronize access to segments, okay? So many readers do not block. You can have, as many readers as you want, as many as you want that read from the same segment, but every time someone writes to the segment, he takes an exclusive lock, and no one can read at that time, and no one can write at that time, okay? We have quite an interesting statistics here, allocated bytes, segments, utilized bytes, overhead bytes. Those are the bytes for indices and all of that crap. Segment count and node count and all of that stuff. So, and we're out of time. Let me show you quickly how it runs, how it works. Okay, so I have this garbage test, manual tester here, and of course pile is covered with many unit tests, and I'm showing to you the graphical manual test so I can illustrate how it works. Okay, so what we do, I'm gonna put, you know, some information here. So this is how those pile pointers look when you do to string on them. And then if I read it back, let's read something like 500,000. Let's read 500,000, and just probably because I do screen capture, I usually get around 800,000 transactions a second on a single thread. You know, for the context switching, you see this number jumps back and forth. And when I do it, I get my object back, and I just print it out as JSON here, so I can see. You know, I select the pointer here that I want to look at, and here is a bigger object. So those are different objects here. So I allocated 23,000. So let's do this. Let's put this favor speed, and I'll explain it in a second. And I do, let's say 11th. That is probably going to crash the video recording. Let's do 4 threads. 500,000 objects each, and I'm gonna put the parallel put, and it did 1 million inserts a second. Okay, and I have 2 million objects here. And then if I do my GC is instantaneous. Let's do another set, and I click the button again, and I have 994,000 this time, and I have 4 million objects. Let's do this. Let's try to increase this number. And my video probably stalled. I'm sure it has, because I'm running video capture here. 9 million objects. 9 million objects. Let's do 6 threads. So the performance here is actually, what happens now is that I put all of the objects in the same segment, and that's why you have a lot of lock contention. Now, if I allocate the pile and I delete some and then I start putting objects back, my throughput is going to be somewhere around 2 million inserts a second. Now think about it. 2 million business objects. Now what business objects? Let's look at them here. Have them here somewhere. Person 2, make fake people. Okay, here they are. Okay, here's my fake person. ID, first name, date of birth, balance, data, some objects, array of objects. Oh, wow. I have an array of objects here. Okay, so it even uses some object graph here. Okay. Oh, here. I was testing this data. Okay. So that, of course, affects the speed, and then some binary data is byte array, and I can populate it just to create some chaff, in the memory, just to add it some weight. Person 2 has even more. It inherits from person 1, and it has even more, dummy fields in here, and they populate with some crap. So that's my test data. And now when I try to read it back, this is the retest is, like I said, this is single thread. A parallel get, I don't remember what it does. Okay, 2 million reads. Oh no, I should have clicked this button here. 2 million reads. Okay, 2 million reads a second. It gives me back the original object, so that counts all the serialization, deserialization time. So this is really efficient. So another trick I can do, I can activate this automatic insert, and then this shows you delta, how many records have, for every time it samples, it shows you how many records have been added. Okay, so we're at the 19, 20 million objects, 21 million objects, and what's going on here? This is probably going to kill my screen recording. I do a garbage collector and still instantaneous. This does full garbage collector. 10 milliseconds, 13 milliseconds. So, and then let me terminate it. So I'm 39, you see the memory barely moves. You create a test application and you try to allocate 39 million persons, and you let this application sit for a few hours, and then you try to allocate more. See what common language runtime is going to do to you. It will start pausing you for 10 to 20 seconds. It will do a full blocking garbage collector when it will approach the threshold. Why? Because it needs to scan that many objects as can. It's just physically impossible to scan that many objects. Now, what we do in the pile, we relieve the garbage collector, because right now for the .NET, for the CLR, it only has how many segments? 13. It has 13 objects instead of 39 million. And then we sub-allocate those segments by hand within our memory manager called NFX Pile. It is a 100% free code, Apache 2 license. You can access the code on GitHub. Oh my God. Okay, code NFX. And you get the code. It is under the application model pile. Here is the pile, all of the interface and implementation. There is even more precious thing called cache that allows us to have indexes and keys and expirations, but I'm going to talk about it some other time. And thank you for watching, and let me know what you any other questions you have. Let me know. Shoot me an email or comment to this video. Thank you.